Today, on the Dilidat, I'm going to be abusing professional grade Cree LEDs.
Here I have two portions of LED modules that are cut out, and each one of these LEDs are in parallel with one another, so they take about 3 volts to run. Here's the 2014 variant. They're both made by Cree. See, so about 3.5 volts, get a warm white glow. And on this one, a 2013 variant, the same nice warm glow. Why am I showing you these? You might be asking. Well, take these two. So, LEDs are pretty complicated things, but some of the LEDs get even way more batty than you might even think. So, here I've got an LED section, and you can see it's lighting up pretty well. So, what I'm going to do with this is take out the tools of abuse, and I'm going to just kind of cut that top portion off on some of these. We'll see what happens. So I've cut those off, and it's kind of like a puttyish kind of material that has the phosphors in there. And I'm going to put power back into here. We're going to see what happens. Connect, make contact. Oh, reverse bias. Okay, now let's see what happens. So, of course, as you would expect, those LEDs no longer work. Check this out. So I've got another section here, and this is the 2013. So you can see that all these LEDs work. And I'm going to do the same thing. I'm going to take my box cutters. And I'm going to knock off the tops of these as well. So, off with that one. Off with that one. Yeah. See what I'm doing? Off with that one. Come on. Off with that one. Goodbye. Off with that one. Okay. Cool. We knocked a bunch of those off. Oh, let's hook this one up. Yeah. That's quite different now, isn't it? Take a look at what's going on. Here we're looking at one of the 2014 LED strips, and here's one of the LEDs. We can see the phosphorus coating on the top. And along the one side here, I'll bring it to the center of the screen, we can see the little reverse protection diode and the wires that go to that and the LED. So let's go over to another one of the LEDs you can take a look at. Kind of skip that one and go over to this one. We can see the wire that comes off the reverse protection diode, and it goes on to the gallium nitride LED. Get a closer view on that. I'll switch focus. Alright, so in the center we can notice that the gallium nitride is a little crystal that sits inside, and there are little bits of phosphorus that go around it. Now on this particular LED, and in most LEDs, the electrical connections are made by two wires that go either on the top of the crystal, or one connection that's under the crystal, and one wire that goes up on top. Many of the commercial 5mm LEDs, 3mm LEDs are built this way. So the 2013 model, the year before, had a different type of LED assembly, and the LED assembly actually didn't have any wires at all, which was a really robust assembly. Let's take a look at that. The 2013 model, and we can notice that there's a couple of differences. It's still mounted on a ceramic block, but there are metallized connections on the ceramic surface. Go into higher magnification here. So those metallized contacts on the ceramic are what delivers the power to the LED, instead of having little wires on the surface of the LED die. We can see that there is a little copper point right there, a little via, that sends the power up to the top of the ceramic, and there's another one somewhere, probably under one of the LEDs. But the electricity is delivered to the LED dies that way, instead of little wires. So that means these LEDs will still get electricity into them, even without the phosphorus coating. So let's turn on the LEDs a little bit, take a little closer look at them. Okay, now I want to point out that there are these dark points in the LEDs, and I believe those dark points are where the connectivity is sent to the top of the LED. So there's got to be some sort of a conductor material inside of the LED or the other side of the junction that is routed through the actual LED die itself. Let's get even closer. So here we have about 4700 magnification, so for about 5000 magnification, and we can see the LED die and the LED die structure a little bit more. And you'll notice that there are also different areas of glowing material. Well, those are the phosphors. So all white LEDs, regardless of their color, start off as blue or violet LEDs, and the phosphor that's added to them is what gives them their either warm or cool characteristics. Here we can see some more of the LED phosphors here, and those phosphors are added together in different combinations to give that correct color. So you'll notice that there are yellows, greens, and orange coming out of the LED phosphors. Depending on the ratios, you get your different color saturations per your LED. Here's one of the LED strips with all the phosphorus tops taken off, and it's this wonderful purple glow. Now, I've not seen LEDs quite sold like this with this color, and it's a really interesting and bizarre color to see coming off an LED. Now, that's because it's not like a UV or purple LED being the 400 some nanometers. It's actually blue LEDs with the residual phosphorus still left on them. So there's still a little bit of glow from other colors coming off. That's what gives it the ambient purple color. And that is a wonderful color. Here we have two of the LED strips, and it's nice, soft, warm glow. Gonna turn off the light. That's very, very nice. Very nice, soft, warm glow. If I can show ya. Nice, decently warm glow coming off those LEDs. We can fix that though. I'm not a fan of warm white like some other YouTubers are. That's okay. We can do a durability test. I've got tons of these. More power. And we'll start a time lapse on this too. Okay, that's cool. Okay, you see that LED flickering? See, I can't see that flickering. The camera sees it flickering. Already looks like the 2014 LED strips are starting to fail. Cool. Continuing on. Okay, the LEDs up here are literally so hot that I can just flick them off. They're hot enough to unsolder themselves and still work. That's incredible. More power. Oh. Yeah, those ones don't like overvolting. Well, I have to say overall, the 2014 did better than the 2013. Remarkably, after a little bit of time cooling down, all of the 2014 LEDs came back on. Yeah, clear winner. 2014 LEDs, good job. So here's one of the 2013 LED models, and next to it I have an absolute behemoth of an LED. So this is another LED. I also believe it's manufactured from Cree, and it was found on an Orion Energy Systems board. And this LED is absolutely nuts. We've jammed over 20 electrical watts into one of these, I mean, if not more. So I kind of want to see what these look like when they're blue, and how much abuse these LEDs can take. I've got some LEDs that are pretty damaged already, so we can take a look at those, see what they look like. Here's what one of those behemoth LEDs look like with the phosphorus coating taken off. The die is ridiculously huge. You'll see 9 points as well. I believe that's where the contacts come up through the LED die and send the current to the top of the LED grid. See if we can get a closer look on that. Higher magnification. Okay, so I have to stand away from the microscope just so it doesn't move. But you'll notice that there's kind of a grid around that little circle. Well, that grid is on the surface of the LED, and it does two things. One thing that it does is it's probably a more conductive layer that goes over the surface to help with the conductivity overall. And the other thing that it does is it helps ensure that the phosphors stick on the surface of the LED. So I'm going to put some power into the LED and get some microscope footage of it running, and hopefully we can see a little bit more of the properties of the LED during that point. We have a little bit of power going to one of these LEDs. Now we can take a little bit of a look on how it glows and what's going on inside. So we can see that there are dark areas where the 9 points are. So yeah, guessing those are conductive pathways. Get a little bit of a closer look on that. Oh, because it's a light source, we should be able to get really close now. Here's one of those 9 dots under extreme magnification, about 5,000 magnification, and we can see the surface of the LED a little bit more, that surface grid kind of pitting. I'm going to roll through the fine magnification knob as carefully as I can. That's cool. Lots of engineering in that LED. Here's the most severely damaged LED that I have, one of the high-powered ones. And I've got it connected to, yes, what might be considered overkill, which is the heatsink, the fan, the thermoelectric junction, and a copper base plate. Will it flam? So I got my power supply here. It's capable of dumping about 4.5 amps, 20 volts peak. However, I think we're going to lose amperage before we lose LED. So I'm going to set this little piece of cardboard right over the LED just like that. And we can watch the current on here, and we'll see if this flams. We'll see if that jams. Oh, off of the light. And we're running about 2.6 volts right now. So 0.35 amps, 2.6 volts. Let's turn her up. Oh yeah, maxed out on the current. Go! New setup time. So let's get everything pre-cooled. And here's what I have. So I have a freshly charged lithium-ion cell, and that will be my source of power, which give me forward current capabilities of about 25 amps. Of course, it limits my voltage to about 3.8 volts because, well, that's the dropout voltage of the lithium-ion cell, but we won't lose the current, which is important. So let's see what current we're getting. my meter here, and we'll just plug that in. Okay, 2 amps. Don't know what our voltage is. Let's try to burn things again. We're gonna need more power. That's a broken LED too. That's ridiculous. More power time. I've already run out of current on my power supply, and I've run out of voltage on my lithium ion cell. Now you're understanding exactly why I have the big heatsink and I have the Peltier junction. So I have the current here, and I have connected up the LED to the 5-volt line on the ATX power supply, which is capable of putting out 22 amps. So I don't think I'm going to run out of either voltage or, amperage. So hopefully we won't get a drop, and we'll be able to tell how much current is going through here. Now as the LED warms up, because it's coefficient to temperature, it's going to draw more current, so that's why I want to keep it as cool as possible. So I'm going to go fire this up, and we'll see exactly if the LED blows or glows and how much current it's taking. Interesting. So there you saw a nice color shift. Alright, now we got the whole setup. Obviously we're not losing current, and we're not losing voltage too much. We've already seen that effect. So we've got a new thing to burn here, and something is going to give. It just is. Let's face it. So let's turn off that light, and we'll see what the thing that gives in this situation is. Here's one of the LEDs before it's subjected to overcurrent and overvolting. Now let's take a look at something interesting. Here's what it looks like afterwards. So that you can see the entire crystal seems to go completely transparent. That is cool. Let's take a look at it closer. Now we can see some of the details of where it's connected on the ceramic base. How these connections are formed. That's intriguing. I did not expect the crystal to go clear like that. See if we can get to a deeper magnification, see exactly what's going on. Interesting. Very interesting. I did not expect that. So we have a 10 ohm resistor on the 5-volt power supply, or 5-volt rail on the power supply. Turn that on. The light. So right now it's 0.2 amps, so about a quarter of an amp going through. And I've got a pair of 0.7 ohm large resistors, 20 watt resistors. So I'm going to bridge the 10 ohm, and we're going to get quite a fair bit more brightness. And it goes up to about 4 amps. That's a lot of power going into that LED. A little paper. See what she does. Oh, that resistor is already warm. Let's add on a 0.8 ohm resistor. Oh, that was it. It had a failure in the LED. So it turns out the LED was perfectly fine. The solder connections failed. Yes, that's right. Even with a massive heatsink, fan, thermoelectric cooling, everything, yes, the LED still got hot enough to desolder itself. So, after some soldering, I get to plug it back in. And we're going to try this again. Alright, and put on the other 0.8, see what it does. 5 amps. Okay, I don't want to be that close to glass that hot. Would you just stay? Alright, and drop the 0.8 in there. 5 amps. Burn! Oh, that is so bright. Let's all wire it up and see what kind of watts we're pushing through that LED. Okay, let's see what our voltage is on that. We are running with that drop. Oh, that's current. That doesn't have anything. Alright, back over the volts. Alright, let's check the voltage we are at. .66. Okay. More resistance. Uh-oh. I have killed something. I have restarted the LED. I'm just going to let this frost over, so that way we can get a momentary voltage range and compare the voltage and the amperage that goes into this LED before the wire unsolders itself. Alright, now it's cooled down. We can get a voltage reading on that with our resistor load. Right, here we go. That is bright. Okay, what was that at? 3.7 volts at almost 6 amps. That's a stupid amount of power to put into an LED. Okay, well, it should burn something, right? Well, let's get some fresh victim paper here. Away. There we go. Oh, we have a catastrophic failure. Oh. That damn wire again. Now that we have seen one of these little LEDs take nearly 20 watts of power, let's test out its bigger brother. So this is a little cob and it's on ceramic, and I don't want to break one of these because they're really nice LEDs, so I won't be overpowering them, but let's put in the appropriate power and see what happens. But first, a trip underneath the microscope to take a look at the little LEDs and the wires. This is what the larger Cree looks like underneath the microscope. We can see all the little LEDs in series, and there are sections of 12. So about 3 volts a piece equals 36 volts, 3.3 volts, 36, 38, 40 volts input forward voltage on these LEDs. 1, 2, 3, 4, 5, 6. 6 rows, maybe 7. No, about 6 rows looks like. So 6 in parallel of 12 in series. That's a lot of LEDs. Okay, obviously it was just bigger time. So we got one of these bigger Cree LEDs, and it takes 36 to 38 volts at 1.4 amps. So a little bit more power. Let's see. Off of the light. Turn up the voltage. We'll put this little glass base on there. As to... God, I can't even look at that now. And burning material. See what happens to that. And what do we got for current? Higher. .9. Oh yeah, that's some power. Still no flame though. Whew. Yeah, I think we know where this is headed. Right there. And power. Oh, holy damn. freaking gnarly. Well, stay tuned for more.